Thank you all for coming. This is a paper about a thesis that I performed with Nolan Conway and Matt Weckler at Webb Institute this past year. I'd like to thank our advisor, Dean Warner. He was a professor at the time, now he's a dean. He's moving up in the world. And Dr. Charles Corrado at Applied Physical Sciences for his sponsorship of this project. So when we were starting to pick a thesis, we got really excited about autonomous vessels because there's a lot going on. And we get to program and build and write paper, and so there was a lot of different stuff to do. So we wanted to build and design an autonomous vessel capable of crossing the Atlantic at a manageable cost and produce a program that was available in the open source environment that could be shared with other schools and other students that want to work on the same kind of project. I'll talk about the background and the theory of our design, the construction procedure we used, the results, and offer some conclusions, and then take all the questions that you can pepper me with. So if you were in the last presentation in here, you know what an autonomous marine vehicle is, but it can operate without human input, but does require programming previous to performing the mission. Can be propelled by multiple means, and is especially useful in harsh environments or to perform repetitive tasks. So humans aren't great at repetitive tasks. We get bored easily and forget what you're doing, and performance goes downhill. So autonomous vehicles are really good for that kind of thing. The Microtransat Challenge was started in 2010 to foster technological advancement in autonomous vessels. And the goal is to build a vessel that can cross the Atlantic Ocean by itself. So far, no one has succeeded. This is the U.S. Naval Academy's About Time, thank you. And they've been very successful recently. They haven't made it, but very successful.
But the boat's right out there if you haven't seen it.
The boat is in the lobby, and that boat that I just showed, and I'll talk about it more in a minute here. The challenge is approximately 3,200 miles between start and finish line, which we estimate about 90 days, but that's plus or minus maybe 100%. So. This is the approximate west to east course. The green line on the left is the start line of the race course, and the red line is the finish line. And the reason the green line's so far off land is because of collision with other vessels. The red areas are geographic boundaries. We didn't want our vessel to sail there because it's out of the way on the way to Ireland. And the yellow areas are fishing or offshore oil drilling areas, where the risk of colliding, as I'll show in the next picture, is pretty high for a small vessel. So there have been multiple past attempts, most recently the U.S. Naval Academy, a boat time that you can see out there. And they were doing incredibly well, heading west to east, until they got picked up by a scallop dragger in the fishing area there, and that's why they started doing circles. That wasn't a problem with their programming. That was actually being in the net of the dragger. Team Joker, which we affectionately nicknamed a bloke in a garage in England. No offense, but he's a very nice guy. He's made 3 or 4 attempts now, I think. Failure methods are unknown, but this is the most recent track in the south coast of England. And then the most successful vessel in terms of time at sea and distance traveled was the Pinta in 2010. She sailed for 18 days, but none of it was really in the right direction. This is the west coast of Ireland. And they were attempting to go west, and they drifted north. So the problem with this is that this vessel was lost at sea, and it's typically pretty hard to determine the means of failure for the vessel if you lose it. In terms of operating environment, average wind speed in the North Atlantic is about 8.5 meters per second. Average wave height is about 2 meters. And if you're traveling from west to east in the summer, that's generally a downwind following sea. However, if you consider a 2-meter vessel and a 2-meter average wave height, you're basically encountering a rogue wave every wave, which is hard to design for. This figure shows the average marine traffic over the course of a year, where red is a higher traffic density. The green line and the red line are still the start and finish line of the west to east transatlantic course. As you can see, there's a ton of density near the coastlines. But if you can get the vessel out towards the start line, the chance of collision is greatly reduced. So to begin our design process, we started thinking about the operating environment, as I just said, and then what the requirements for a vessel to successfully perform this mission would be. And first, self-righting. I mean, if you're going to experience a rogue wave constantly, the vessel needs to come back up. You need to be able to sail upwind. Even though the course is generally downwind, you don't want to lose ground when you're faced with a headwind. We decided to use a wing sail, and I'll talk about why we used a wing sail later on, but we wanted a vessel that integrated well, and that means Generally small, not a lot of roll, period, not a lot of roll, so that the wing remains efficient and near vertical. You need significant deck area for solar panels because we're not putting a nuclear power plant in and we need to generate power on the way across. And then there's significant marine debris and seaweed that you want to shed. And you want a vessel that's pretty simple to build and operates simply so there's less parts to fail on the way across. So we started with a beautiful, traditional, looking at a traditional hull form, traditional sail plan, a full keel vessel that has great seakeeping and self-righting characteristics. But it doesn't have a lot of deck area for solar panels. Then we moved on looking at modern catamarans. I mean, this is a beautiful vessel, but obviously not great in the seaway. Definitely not self-righting, as was shown during the America's Cup multiple times. So we considered, we looked at considering a trimaran, and if you put a full keel on a trimaran, it's possible to make it self-righting, especially if you have some buoyancy in your wing sail. And the great thing about this is you have a nice firm center hull that you can use as a structure for the mast. The cross structure between the hulls can be used to support solar panels. And you can integrate all your electronics into the center hull. There's also lower roll angles to keep the wing sail working effectively. So we created a trade-off matrix, ranking each design characteristic. The trimaran is obviously not the best in every consideration, but it is pretty good overall. So in terms of those hull design requirements that I talked about, we started with a full keel on the trimaran, which is not traditional, but it sheds debris, and it's your keel can't break off if it's integrated into the hull. The stability from the outer hulls helps lower the roll angles, the deck area, the space between the hulls, as I discussed. And then you can put a single rudder on the center hull, and you can put the mast step inside the hull. And we considered this simple, and that may have been a mistake, and I'll talk about why that didn't go so well later on. So the principal characteristics of the vessel: just under 2 meters, displacement of 42 kilograms, and a 40-watt solar array for power generation. So the reason that we chose to use a wing sail, soft sails have benefit of historical performance. We've been using them for thousands of years and they work fantastically. However, when you don't have a crew on board to maintain the sails, there are some issues. And we were concerned about the complex control system required to sheet in the sail, and if you want to reef or change the sail area, I mean, it's very difficult to do with an autonomous vessel. This is a wing sail on an America's Cup catamaran, 2-panel wing sail. And this is a wing sail on Greenbird, which is the record-setting land yacht. I believe it went 128 miles per hour under sail power alone. And it uses a rotating mast with a controllable foil on the trailing edge. The advantages of this kind of sail system are that it's quick to respond to changes in wind. I'll talk about why that is when I describe how it works. It's very low power because you're only adjusting the trailing edge foil. You don't have to sheet the whole sail. It's efficient because it has a high aspect ratio. And we considered it pretty simple because there's only 2 moving parts, the trailing edge foil and the whole mast that's rotating. But that may have been a poor assumption. So in a traditional sail, you have the sail creating the foil shape and the wind flowing over the sail. The main sheet changes the angle of attack of the foil, and you get lift. On the right is a rotating wing sail, where the green represents the mast and the rotation point. You have the same lift off the sail, or the main foil, but instead of sheeting with a main sheet, you use the trailing edge foil over here, and that creates lift and can rotate the whole sail around the foil, around the mast. So if the wind shifts, the foils doesn't need to change to continue to sheet the sail to the right angle. The whole sail just rotates until the trailing edge foil is aligned with the wind. So finally we had final wing was balanced, controllable foil. And the structure you see running through the wing is to counterbalance the sail. So when the vessel heels, if you put weight on the front end, you end up with a fully balanced rig, and the vessel heels and the angle of attack of the sail doesn't change. We used a NACA 15 foil shape. So to build the vessel, we started stripping cedar planks. We used a traditional boat building method, and we wanted to build a pretty light hull form, and the hull form had a lot of shape to it, so we wanted easy method to build that. So we stripped cedar planks on the table saw, and we laid out the frames, and you can see our hull form here, based on a J-class, traditional J-class hull form. Nope, apparently you can't. And then we started planking the hull form, so laying the cedar strips onto the mast, or onto the sections, and we went all the way along, and we got up towards the top, and just continued planking. And then these are our videos, but. And then once we were done with the planking, we laid fiberglass over it in traditional boat building method, laminated up, and epoxy and painted, all normal stuff. To make the mast and the sail, we used a carbon fiber tube as the center of the mast. And the sail is constructed of foam foil sections with wood shape every 3 or 4 sections. So we cut those sections all out, laminated them together with epoxy. Oh, this one's working. Glued it all up, aligned it, compressed it, let it sit, and then faired it into a section, cut it, separated it again, put it back on the mast with the cross structure running in between. So those silver beams, aluminum box bar, connect to the trailing edge foil on the back and the counterweight on the front. And then covered it, fiberglassed it, and faired it so it would be watertight. This is the final wing sail, as you can see, with a nice paint job. Paint makes everything look better. And the counterbalance is on the right side here. The software for the vessel was developed in C++ and compiled using Energia to send to the microcontroller. So from the computer going to the microcontroller, and then microcontroller I'll talk about in a minute, but the sensors coming into the microcontroller were roll and pitch and the Airmar navigation sensor. And then outputs from the microcontroller were the linear actuator for rudder control and a small sail control servo for that controlling edge foil. We used 2 12-volt, 21-amp-hour batteries and a 40-watt solar array. We estimated, based on our power loads, that the vessel could sail for 2.5 days without sunlight until the batteries were completely depleted. And then with the 40-watt solar panel, you can recharge that in about 6 hours, depending on the amount of solar energy you're getting. So the main sensor on the vessel is the Airmar 150 WX. And the reason to use this sensor is that it's ultrasonic. So it has no moving parts to measure wind speed and direction, which really helps improve the reliability. It also has a GPS on board and a compass. And so you can get your location and your heading and your wind speed all from the same device. You also get time, which you can use for sailing logic to determine when to tack if you need that. It's designed for low-power environments. However, it needs tilt compensation. So the compass on board, when you heel the vessel, the third axis of Earth's magnetic field comes into play, and your heading can be off by 15 or 20 degrees. And so the roll and pitch sensor that I mentioned earlier is used along with an algorithm to correct for that third axis. We used the TI MSP 430 microcontroller, very low-power microcontroller. And the reason to use it is that it has 64 kilobytes of ferroelectric memory, so it can maintain your program even when it completely loses power. The program went basically like this. First, you establish communication with the sensors, determine the wind direction, set your course to the next waypoint. Waypoints are user input. And then the vessel decides whether or not it needs to tack to get there. So there are 2 main reasons that the vessel would need to tack. One is a boundary limit. Those red areas I showed on the figure earlier on, we don't want the vessel sailing to Nova Scotia when it's trying to go to Ireland. So you set a boundary. The boundaries also help keep the vessel from going into dangerous areas like oil fields or high traffic areas. Then you want the vessel to be able to tack when it gets to a more optimal angle on the other course. So the vessel can determine whether essentially it's being headed, and to get to the waypoint it should tack and sail the faster course. Finally, you want the vessel to switch to the next waypoint. When you're doing long distance navigation, there's no reason the vessel needs to get to the specific waypoint in the middle of the Atlantic. It's a meaningless point. It's just on the way. So we estimate you want to switch when you get somewhere near 200 to 500 miles from the waypoint and start heading to the next one. So let's talk about the results. We had some success. It was marginal. Here's the vessel. It floated, so that was good. there were some serious mechanical failures that we didn't end up having time to correct. The main one is mast step friction. So the mast is a cantilevered beam and supported in two places inside the vessel. We use plastic sleeve bushings to support the mast. It needs to rotate freely, but you don't want corrosion in a roller bearing. So we chose sleeve bushings at the time. We can ask questions about why we did that and whether that was the right decision. There's also a packing on the mast, a plastic ring packing to keep water from entering the hull through the mast. And both of those things created significant friction, which makes it hard for the wing sail to rotate as needed and power up. We also had leaks on the hatches and some cross-structure torsion issues. So reasons for the failure, and I'm going to call that lessons learned to be a little positive here. We set pretty big expectations for ourselves. There are three people. You can see Matt on the left and Nolan working here, testing the vessel on land to test the programming. So we'd set waypoints on land and drive and see if the rudder would try to convince the vessel to go the other way, and then tell the car driver to turn the car the way the boat was telling him to go. We had 3 people in 8 months, and while we were really excited about the project, we also had other work to do for the full course load, and then it was hard to keep motivated. Also, we spent a lot of time engineering things when I now think we should have spent some time just mocking up a prototype and building them and testing them right away. So, for example, the mast step. We spent a lot of time working with manufacturing people at Webb to help us figure out the best way to build it and design it and what was going to work. That took about 2 months, and then we're running out of time to go back for the second level. It's also hard to build reliability into a design when you're working at a low cost and a pretty rapid prototyping process. So we had problems with our power distribution system based on the reliability of the distribution chip we were using. So if you look at this like a prototyping process and that this is the first prototype, then I'm pretty happy with where we are. If you look at it like the vessel crossed the Atlantic, no, it didn't cross the Atlantic. And with that, I'll take questions. Thank you all for coming.
Would you like to handle the questions?
Yeah, sure. I'm repeating them for the microphone. Okay.
Questions?
Wow.
Yes, no, them. So what would you do differently, straight up? Any changes in hull design?
Definitely. We definitely need a deeper keel. Definitely. I mean, stability is hard to come by. The mast is way up there, and you have weight growth throughout the design process, of course.
Did you do a self-righting test?
We did. We did. Yes. It did not self-right.
You see, those are great videos.
We did a lot of modeling. We did a lot of modeling and using GHS essentially to invert the vessel with our weight estimate and see if it would self-right. And then we did it with the actual vessel. But initial weight estimate compared to the finally designed vessel were off. Andy.
So, I mean, you mentioned that it didn't get very far. How far did it go? Was it able to perform at all, even start moving?
The question was, how well did the vessel actually sail? Yeah, you get lift off the foil. The problem is, if you put the foil in, manually could move the foil, like the wing to the right place, you would get lift. It would start moving, but the problem was the trailing edge, there wasn't enough area or the friction was too high to rotate the sail into a position automatically. It can steer. That part worked, so we really just had trouble with power there. Yes?
When we did a design for an autonomous sailing vessel, we had a mast that was fixed, didn't rotate, and then the wing hung on that so that you could then turn the wing. Most of the weight was at the top, and we just had like Teflon bearings at each of the frames there.
Right.
So you didn't have the problem with water getting in.
Right.
At the mast.
So that was an initial consideration, and the reason we chose to go with this method, so we had a slip ring with wire connections in it at the bottom with, just brushes, to run the signal up to the servo that was controlling the trailing edge. And so that's why we had the mast rotate, because you could put the slip ring in the bottom and run the wires up in the mast. And so the wires in the mast were essentially stationary, and the wires coming out were essentially stationary. And we couldn't figure out a way to have I guess you could have used a different type of slip ring with brushes to transfer that same data to the wing sail out of the mast.
Yeah, we had the slip ring at the top.
Okay, right.
where it's
And you ran it over. Okay.
prior.
Right. That's something I would do differently.
Good answer.
Yes.
How long do you think we'll see the first successful transitors across the Atlantic?
The question was how long until we see the first crossing? Well, I think Saildrone, which is a California-based company, I think that they could do it. They have a vessel that looks fairly similar to ours. They're a commercial company and they don't share information really effectively. They don't like to. But they have sailed from California to Hawaii, and pretty quickly, with an average speed somewhere around 5 knots. Their vessel's much larger. I think if they wanted to risk their prototype and their vessel out there, they would have a pretty high chance of success. But it's a big risk for a commercial company to send the vessel out there. And that's part of the reason we didn't send ours, because it's valuable and Isaac's going to keep working on it, trying to make it better. Yeah, that's on you, Isaac.
Saildrone is actually attempting a round the world sail.
Are they? Yeah, so
Even
they think that they can do the Atlantic and a lot more. Yes?
You mentioned another school or another team that whose voyage was interrupted by essentially traffic and
Yes.
unexpected obstacles. What did you have in your design to think about or deal with that?
Our main goal for avoiding collision like that was avoiding the areas that have high traffic. And then the plan was for, if we were going to launch the vessel, to use like a larger vessel to transit it out of a high traffic area and avoid the fishing zones. The team is the U.S. Naval Academy, and he's a little more qualified to talk about that than I am.
In that case, did you even get picked up in one of these high traffic areas? It seems to me across the Atlantic, even a low probability event recurring over and over and over again.
So we were picked up twice in high traffic fishing vessel areas.
So it wasn't high traffic areas.
It wasn't, yeah. And in fact, the first time we were picked up, we were 5 miles from the edge of the far edge of the fishing zone. So we were starting to get excited. The second time, we were actually not going in the right direction, and it actually sailed into the harbor where they were docked.
So
That was a little more understandable. But we've actually gone with big ocean concept. Is we talked with the fishing fleet, and they told us where most of their traffic was, and we tried to go around that. But you can't say exactly where all the ships are going to be, because there are an awful lot of them.
So we considered putting an AIS receiver on the vessel so you could figure out where traffic was coming from. But the problem is it moves so slowly, you really don't have an avoidance plan. Like by the time, if you see a container ship 20 miles away, it comes up on AIS. That's about the range you can pick it up at. The container ship gets there in an hour, and at 2 knots, you've gone. Maybe you got out of the way, maybe you didn't. So, but that is definitely future work on the subject. Yes, Paul.
Did you have a chance to test it in really high waves?
We didn't get that far, no. The small waves you saw were trouble enough.
So you know what I think about power supply, but 2.5 days is not long enough in the North Atlantic to predict for sunshine. So do you have recovery? Would you just sit there until?
Right, yeah. So the reason that microcontroller, we chose that is because it can lose power and then recover to the same, and remember what its waypoints and what its program is, and try to move on to the next. But definitely 2.5 days with, obscured coverage. It would be nice to put solar panels on the wing too, because that's a great area, but that was beyond our costs, our economic option. Yes?
What was worse, the power failures or the mechanical failures?
The mechanical failures. The power failures were sporadic. We could control. It was just a problem with we were using a cheap Polo power distribution board that had some programming issues. The mechanical failures were this mast step needs to go back to we need to make another prototype of the mast step, essentially. Yeah.
2 questions. Did you have any way of receiving data from the vessel while underway? And second, for you or Isaac, what are the future plans for this vessel?
Yeah, so it's pretty common to use a spot tracker, GPS tracker, which is a standalone device powered by 2 AA batteries. You can set it to update every 6 hours and send you a position. To send more data than that in the North Atlantic, you need to pay for some really expensive satellite service. And we didn't get that far. I don't know what Isaac's plans are. I'd like him to work on it as possibly a thesis. Isaac, you want to comment on that?
At this moment, I'm currently planning on to continue work on it as my thesis. I haven't put too much effort yet this semester into it, but I plan to start soon on it.
Okay, so you're not currently working on it as a thesis, but in the future.
Yeah, he's a junior, so we get another year. Yes?
Did you get funding?
Yeah, so the organization I mentioned at the beginning, Applied Physical Sciences, Dr. Charles Corrado, supported us. So the budget was around $4,000 for this project. And we didn't pay ourselves. Definitely. But we were under budget. I mean, it doesn't matter if you don't. Anyway.
All right, Satchel, thank you very much.
Thank you.